very happy to have you for the SSDan 2025 webinar series on analyzing the Census and American Community Survey with R, with Professor Kyle Walker, who is at the Texas Christian University, professor and chair of his department. I'm Bill Fry with the Social Science Data Analysis Network at the University of Michigan. And this is the first of 3 webinars we're going to have on Wednesdays, today, next Wednesday, and then on the 26th, 2 weeks after that, on different aspects of analyzing the census and ACS with R. They're each going to be 3 hours long, and they're all going to be self-contained. The first webinar today deals with using R and tidycensus to analyze the 2023 American Community Survey. As Kyle will tell you, it's one of the most extensive census products that there is. And in the last 2 months, these new data have been released, so you'll be able to learn all about this very quickly. The second webinar is going to be a week from now on the 12th. Wednesday, the 12th, where we'll talk about the 2020 census and how to analyze it with R. And then 2 weeks after that, on the 26th of February, we're going to be talking about mapping and spatial analysis with R using all kinds of data sets. This is a very popular series. I think we have almost 1,000 registrants for today. And the reason is because we have Kyle Walker. He is the expert on using R in analyzing census data. Not only has he do this analysis, he's created all kinds of programs and techniques to be able to do this easily. A lot of people know about R, but not too many people are expert in using R to bring census data into their analysis, and this is what he has done. He's also the author of this book, which you can get on Amazon. It's called Analyzing U.S. Census Data, Methods, Maps, and Models in R. You don't have to buy this book to use these seminars, but it could certainly help you if you wanted to. So what we're going to do today is talk about, the 2023 American Community Survey and using R with some of the tips and tips and tricks that Kyle has put together. And the good thing about Kyle is not only is he knowledgeable about that, but he's an excellent teacher. And that's why we have so many people signed up for this. So we're very happy to have him here. A little bit about SSDan, the Social Science Data Analysis Network at Michigan. It's ssdan.net if you want to look it up on the web. We've been around for about 30 years, and what we try to do is make census data available to students, to teachers, to researchers in all kinds of ways, beginning with introducing census data for the very first time in an undergraduate class, all the way to graduate students and researchers. And I think what we're offering today is good for all of those audiences. So you don't have to know anything about this to get something out of it. If you do, if you know a little bit about R, if you know a little bit about the census, you'll get a lot out of it too. But if you're just starting from scratch, that's fine. In fact, we're going to make these webinars, each of the 3-hour webinars, available via video, so that you can go back and look at them to sort of catch up on things or to reiterate things that you wanted to see. So I think you're going to find that all of this is going to be very useful. I'm not going to waste a lot more time except to say that this is a 3-hour webinar. We're going to have a 10-minute break after each hour to get people to sort of maybe grab something to eat or just relax a little bit. And then we'll be back and we'll be done at 3 p.m. EDT. So thank you for coming. We appreciate your being here. And I'm now going to turn things over to Kyle Walker. To you, Kyle.
All right. Well, thank you so much, Bill, for the generous introduction. I really appreciate it. And I am absolutely floored at the response to these webinars. I am very excited to be able to spend this time with you. This is by far the most registrants we've ever had. Already we have almost 400 of you in the room. That is by far the most that we have ever had attend a single webinar in the 5 years that we've been doing this. And I have really appreciated the partnership with SSDan over the past several years because we see this as a very important public service where census data are foundational to so many different workflows around around the world, certainly around the country, and in many of your jobs. And these webinars as well are particularly timely, especially in the past week or so, where there have been a lot of questions raised about the availability and stability of some of these resources that we rely on for our work moving forward. And so, what I'll be trying to do, and I'm happy to answer questions about it, is introduce you to resources that are available um, for you all to use right now to do your jobs and get access to the data that you need, and also be on top of things with respect to any changes in data availability that may happen, and make sure that you know where to look. And so, with that said, let's go ahead and jump in. I am going to share a few links with you as we go for resources you can use to get in touch with me, to get access to the webinar materials, and follow along. So I'm going to go ahead and share my screen right here. All right, you should now see my screen. And what I'll be doing is flipping back and forth between my slides and our studio, which is the software environment I will be using to demonstrate some of these concepts and workflows with you. And I'm going to step you through briefly how to get access to those materials so that you can follow along. Some of you will just want to watch and you can come back to the recording later. Some of you will want to follow along live. Again, either way is totally fine. You may want access to the slides. The slides have embedded R code in them that you can copy paste. If you have R installed, you can copy paste into R. Or if you don't have R installed, I'll give you a solution as well that you can use. So keep an eye out on the chat. I'm going to paste here a link to the slides. So if you should see that link, if you follow that link, you will be able to access the exact slides that we're looking at here. I also want to share with you the materials. So the materials I host on GitHub, I will be posting the various webinars as we go. Certainly, I think some of the content for webinars 2 and 3 are evolving for some reasons we'll discuss. And so I don't have those posted yet, but they will be posted for the next 2 webinars, and those are going to be publicly available, even if you can only attend today. So I'm going to go ahead and share that link as well. You can go ahead and visit that from the link in the chat. You will see this exact same web page that you see on my screen share. And so there are a couple ways to follow along with the course materials. Some of you come in because you're curious about census data. Maybe you are accustomed to downloading shape files or data from the census website, and it's not working right now. So you've come to this webinar to find out more about that. Others may be experienced R users or have been to one of these webinars before and you already have it installed. And so there are a few ways that you can follow along today. So we're going to be using R, which is one of the more popular software environments and programming languages for data science in this webinar. And so R is a program that requires that you use code. So we will be using code to access and analyze census data today. If you aren't familiar with R, you can try it out today. If you're experienced with R, you'll be familiar with some of the concepts. So if you're brand new to R, follow this link. This is a pre-built cloud environment that you can use to get access to all of the materials. So if I jump over there, what you will see is something very similar to this screen. If you don't have a Posit account, it'll ask you to authenticate. You can authenticate if you have a Google account, and it will boot up a project for you. And so what you'll see is the project launch, and you'll see all of the materials that I've shared with you for this project. As you boot it up, one of the first things that you will see is up here, you'll see a banner where my cursor is that says that it is a temporary project. So you're going to want to go ahead and save a permanent copy, and that'll save that in your Posit Cloud account. That will give you permanent access to the files. I notice if some of you may be trickling in and you don't have full access to the chat history, I'm going to go ahead and just repaste the GitHub link and the link to the slides. I'll also paste as well a link to the Posit Cloud environment. You can go ahead and log in there. And one of the great things about this environment is you get a pre-built environment. So something that can be challenging when you're getting started with R is you have to install things. I've already installed everything for you that you need. And so you'll see a script editor here. And what you can do, and I'll walk you through how to run all this code in just a little bit. One thing that I do is, and I'll be working in my own version of RStudio today. I like to have this console over on the right. So something, if you want your Posit Cloud to look exactly like my environment, you'll click the Tools drop-down menu. You'll click Global Options. You'll click Pane Layout, and you'll make sure to put the console on the upper right. That'll make it look like what I'm doing. So that's one way that you can follow along. If you prefer to work in your own version of RStudio and you already have that installed, or maybe some of you are power users and using a different IDE like Positron, there are a couple different ways that you can get access to the code. So if we go back here to the GitHub page, if you're familiar with Git, you can clone the repository to your computer by using this command in a terminal. If you're familiar with R, but not comfortable with Git, you can navigate to this folder and you can go ahead and grab or copy paste all of the code, which is located here. So you can download this file by clicking the download button, or you can copy the file and paste it into the script editor in RStudio or Positron or whatever it is that you're using for your work. So I want to make sure everybody has a sense of how to get up and running. I do see one question. Do you need an account for Posit? You can sign up just with an email if you want, or you can authenticate. If you have a Google account already, you can authenticate with that, and it's totally free. So there are paid tiers, but you're not going to need a paid tier to do this work today. All right, so that gets us up and running. And so what we're going to be talking about today is analyzing data from the 2023 American Community Survey in R. And Bill gave an excellent introduction. Very briefly, I am professor and chair of the geography department at TCU, and I also work broadly as a spatial data science researcher, software developer, and consultant. I have developed a variety of R packages. You'll be learning about the tidycensus package today, and you'll be learning about, at least one of these other packages in a future webinar. And a couple years ago, I published my book, Analyzing US Census Data, Methods, Maps, and Models in R, which is also freely available online. So today's webinar is all about the 2023 ACS. We've got a couple other webinars that are going to focus on some related topics. Next week's is all about decennial census data. So we'll have a heavy focus on the 2020 census data, but also we will look at historical data as well. And we'll take a week off, and then we'll come back on Wednesday, the 26th, and focus all about mapping and spatial analysis. You'll do a little bit of that in this week and next week's workshops, but that will be the focus in 3 weeks. And so in terms of today's agenda, we're going to introduce in the first hour, what is the ACS, what is R, what is tidycensus, how do you use it? In hour 2, we're going to cover some ACS data workflows. And finally, in hour three, we're going to look at individual level ACS microdata, which you may or may not be familiar with, but is a remarkably useful tool to gain fairly granular demographic insights about the US population. So we'll jump off and start booting this up. And so, talking about the American Community Survey, what is the American Community Survey? So, the US Census Bureau is best known for, and its most important task is complete enumeration of the US population every 10 years, which is constitutionally mandated and essential for redistricting, and proportional representation in Congress. The American Community Survey is the second most important survey that the Census Bureau conducts, and it's an annual survey of about 3.5 million US households that asks a lot of questions that we don't ask on the decennial census form. And this gets us information about topics like income, education, housing characteristics, language, all sorts of things that are really foundational to a lot of the work we do in real estate and healthcare and business and retail. And you could go on and on and on, social services. These data are foundational to so many of those types of industries and jobs. They're basically used across the board. And so you'll get acquainted with those today. The data are available as 1-year estimates for geographies of population 65,000 and greater, and then 5-year estimates. So what you'll have is a pooled sample for geographies all the way down to the census block group. And you get back from the ACS estimates characterized by a margin of error. And so something that we'll be talking about today is how to get data. And I know a lot of you are attending today, and I already see some questions about this. There has been a lot swirling about data sets being taken down from US government web pages. And so the American Community Survey is available from a variety of different outlets. What's been removed for now, and I don't have a timeline for when it will be back up, are the bulk flat files of the ACS. So if you wanted to go and just download the entire 11 gigabyte zipped American Community Survey, you're not able to do that at the moment. What is available are a couple of resources, and one of which we're going to be covering today. So data.census.gov is the main data portal where you could go. For some of you may have a decade ago used American Fact Finder. Data.census.gov has been around for several years now, and that website is still up, and you can go and browse and download any of the data that you want. Data.census.gov is powered by the US Census API, and an application programming interface, if you're not familiar with that term, it typically refers to, at least with respect to data, a way that data are served such that they can be consumed programmatically or by software applications. And so you're going to be learning how to use the API today through R. And that data is still available as well. So, the ACS, the entirety of the ACS is still available from the census website. You just can't go and download the entire flat files from the FTP server right now, but there are still ways to get it. And so you're going to be learning today about tidycensus, which is an R package, which I'll explain a little bit more in a moment, that interfaces with a variety of different APIs. So you can get access to decennial census data, the American Community Survey. You can get the census population estimates and census microdata. And I'm be covering some of that today. tidycensus has been around now for almost 8 years, which is crazy to think about, but it has been phenomenal to see the uptake of tidycensus, across the art community and the data science community more broadly. It's been downloaded nearly 600,000 times since 2017, including about 100,000 downloads in the past year. So it's really reached a lot of people, which is, fantastic. And this was originally a National Science Foundation supported project that, I'm very happy to make available for all of you. So hopefully it can, ease the burden of working with census data. And so talking through some key features, and I'm going to provide one caveat as we talk through this. So a key feature of Tidy Census is it acquires census data for you from the Census API, and then it wrangles it for you. So it create puts it into a format ready to go for analysis with the tidyverse, which is an extremely popular data wrangling framework in R. One of the main reasons I developed Tidy Census is that it also automatically, or it should automatically download and merge census geometries to data for mapping. I should caution you, this functionality is not currently working because all of the census shapefiles have been taken down. So, that's a caveat. And so I'm sure many of you who are attending today, you have seen that news that the Tiger Line shapefiles, so all the census geographic data from the FTP server is not available. That's what Tidy Census pulls from for geographic data. So you can still get the demographic data, but the geographic data are down. I'm working on some workarounds. I'm going to show you a workaround for that today. But this is a key feature of Tidy Census that unfortunately is not working right now. It also includes tools for handling margins of error in the American Community Survey, working with survey weights in the PUMS microdata. And I do see questions, and I'm going to cover some of these questions. If you're asking kind of how can I get my data, how can I find the workarounds, I'm going to cover that as best as possible, and I'll try to answer some of those questions in the Q&A at the top of each hour. And one other nice feature of Tidy Census is you don't have to remember your FIPS codes. You can just type in the name of your state or county that you want, and it's going to get the data for you. So we talked a little bit about R in our studio, mentioned how we get access to some of those resources. Again, I'm going to go ahead and jump over that. If you're using the Posit Cloud environment, you don't have to install these R packages. If you're working from home or at your office and you're using your own version of R, you may need to run these commands. And so if you go to the R script, I'm going to jump over here. You'll notice that those lines are commented out. And for those of you who are new to code, commented out, we put our little number sign before that because that is the comment operator in R. And functionally what that does is it shows you the code, but it won't execute when you try to run it. And so I'm going to give you a little bit of an overview of how to get started with all of this in just a moment. One other thing to be aware of, and this is something that I'm noticing, is many of you may already have something called a Census API key. So often APIs require an API key to use them. The Census API, fortunately, does not require an API key unless you're making more than 500 queries per day. If you're following along with our work today, you're not going to make more than 500 queries. And so in this particular case, you'll be fine. You can sign up, just Google Census API key to sign up. I do believe that service is currently down. I tried getting a new key just yesterday, and it did not come in. So I have a hunch that that service is also currently down. I don't have 100% confirmation. I do see someone that says it's back up, so that's great news. So feel free to jump over there, get an API key, and then you can set your API key in R with this code if you need it. So that will allow you to query the API more than 500 times in a day, which you may think seems like a lot, but power users frequently go beyond that, especially if they're doing some bulk pulls. So that's something that you don't need for today, but you can certainly grab, and you should grab if you're planning to do longer term work with the API. All right. So let's go ahead and jump back to the slides, and we're going to talk through getting started with ACS data and tidycensus. So your portal to the ACS in tidycensus is a function called getACS. And I'll try to introduce, for those of you who are new to programming, some core concepts in programming as we go. And bear with me if you're new to those concepts. So you can think of a function in an R package as a little mini software program that someone, a developer, has written to package up a whole bunch of code and workflows into a nice little program that you can run. And so getACS builds on thousands of lines of our code that I've written and some of my collaborators have written so that you can get data with only a few lines yourself. And so that's how a function works. And functions have something called parameters and arguments. And so there are two required arguments that you'll need to put in. And that's the geography, which is the level of aggregation of your data, and then variables, which are one or more variable ID codes that you can pull from the Census Bureau that uniquely identify a particular variable that's found in the ACS. And so you'll see a code that looks like this. This is for median home value. And so what we're doing here is, just to talk through it, we're creating an object in R called median value. The assignment operator in R is the arrow sign. So you have your little caret and then your dash. And what this does is it says, okay, make me an object named median value that is the result of whatever this little program is. So get ACS data at the county level for median home value for the 2023 5-year ACS and assign it to this object named median value. And so for those of you who are experienced with R, that's all old hat. For those of you who are brand new, let me show you exactly how that works. So jumping back here, I'm going to go ahead and run this code. I'm going to make it just a little bit bigger for you to make sure that you can see. We're going to load in the tidycensus package with this library tidycensus. So the way that you run code in RStudio, a couple different ways you can do it. So if you put your little cursor right in front of a given line of code, it will run all of the corresponding code if you use the keyboard shortcut Command Enter or Control Enter. So I can do Control Enter, and you'll notice that my cursor runs that line of code, and then it steps to the next piece of code. You can also, if you want to be a little bit more deliberate about it, you can highlight a block of code. You'll notice how it turns blue, and then you can click this Run button. And what that Run button will do is it will send the code from your script editor over here to the console to be executed. And so to show you how this works, I'm going to go ahead and run this code. And so you'll get a message that says getting data from the 2019 to 2023 5-year ACS. And again, what this is, it's a pooled sample of responses between 2019 and 2023 that are weighted to reflect the overall composition of the US population. And so you'll notice here down at the bottom, there's an environment tab. That shows what objects I've defined in my R session. And I have a table of data with 3,222 observations and 5 variables. So if I want, I can print out the first few rows of my data by simply calling that object name median value. So if I run that, you'll notice this is what my data look like. So I have 5 columns here. I have a GeoID column. That's going to be an ID that uniquely identifies that specific geography. So GeoID, so 01001, that's the unique ID amongst all counties in the United States. And so I see a lot of questions coming in. Many of those questions will be answered over the course of the next hour or two. You'll see the GeoID here. You'll see the name, which is how we would commonly reference that place. You'll see the variable ID that you just requested, and then the estimate and the margin of error. And so in this case, Autauga County, Alabama, the median home value was $197,900, and our margin of error around that estimate is $8,280. And we'll explain all that more in a bit. And so when we look, we're going to go ahead and jump back to the slides now. You can take a look at our data. It's the same data that you've seen there. And what we see is that we grabbed data from, and I do see one question about this. How does it know to get 5-year versus 1 year? There are a lot of arguments that you can supply to get ACS that aren't required, but they're optional. And so that means that a lot of these arguments, they have defaults. The default value for the survey argument is ACS 5, which refers to the 5-year American Community Survey. So in this case, the 2019 to 2023 ACS data that just came out in December. If you want the 1-year ACS, which again is released every year, but only corresponds to geographies of population that are 65,000 and greater, you can change the survey value to survey equals ACS 1. And so let's go ahead and try that out. I'm going to jump back over here, run our median value 1 year, and we can take a look at it. So we get the note that we're getting data from the 2023 1-year ACS, and the 1-year ACS provides data for geographies with populations of 65,000 and greater. And we notice here that we only have 649 observations. So there are 3,222 counties or county equivalents in the United States. So we get complete coverage in the 5-year ACS, but in the 1-year ACS, we only get those geographies that are of population 65,000 and greater, and there are only 649 of those in this particular case for the 2023 ACS. And so our values are going to be a little bit different. We're going to explore that in greater detail in just a moment. So at times, you'll want more than just a single variable. And so you can request an entire table of variables. And so you can think of the table that a given variable belongs to as the prefix. So this variable, which references median home value, and I'll explain how you can figure all that out in just a moment. But this references median home value. The table ID is going to be everything that precedes the underscore. So it comes from table B25077, which may have a single variable. It may have multiple variables inside of it. So if we run this code here, and I want to get data on income, and in this particular case, from the table B19001, this is going to give me estimated counts of households that fall within given income bands. I can specify table equals, and I ask for that table, and I make that call. And so if I jump back here and give this a try, you'll notice that it says we're loading the ACS 5 variables from table B19001. And then we can take a look at what that looks like. And you'll notice here that we have what's called a tidy or long form data set where Autauga County, Alabama is repeated multiple times. So here, our first row, we have Autauga County, Alabama, for this variable B19001 underscore 001. And the estimate is 22,523, and the margin of error is 431. A question that comes up is, well, how do you know what that means? I'm going to show you how to do all of that in just a moment. But what these are reflecting are different household counts that fall within different income bands. And so jumping back here, I want to show you a couple things. These estimates can be refined as well. And so we're going to let's talk more about geography and variables in tidy census. So we've been pulling data at the county level. But one of the great things about working with census data is the US Census tabulates data at a variety of different geographies. And so this diagram helps explain some, not all, of the geographies that are available from the Census Bureau for data tabulation. This central axis or central spine of the diagram, that's going to be your core geographic hierarchy of census enumeration units. The smallest enumeration unit available is the census block, which is analogous to a city block in urban areas, though it may be larger than that in rural ones. Census blocks are, again, the smallest geography at which the census tabulates data. And for confidentiality and statistical reliability purposes, you can't get ACS data at the census block level. You can only get decennial census data at the block level. The ACS starts at the block group, which is a collection of census blocks that typically contains, on average, maybe a few hundred to, a little over 1,000 residents. And that's going to be your smallest geography available in the ACS. Collections of block groups make up what are called census tracts, which are a very common geography that we use for representing loosely the geography of neighborhoods in cities. And so a census tract contains on average around 4,000 people. And census tracts then neatly nest within their parent counties. And counties are both an enumeration unit, so we tabulate data at the county level, but they also reflect actual political boundaries. So the county that you live in, that you pay property taxes to, that has a boundary. The census tabulates data at that level. Those then sit within states, which go all the way up to the nation. We then have a bunch of other geographies, and you can get a sense of how they fit within each other. Zip code tabulation areas approximate zip code geographies. Those don't fit within anything. Sometimes they cross state boundaries, but they do fit within the nation. We have geographies like county subdivisions that fit within counties. And we have geographies like school districts, which may cross county boundaries, but fit within states. Same with congressional districts. So all of this is available. But looking at this diagram, you can get a little bit of a sense of how that works. So how do you understand how to put all of this in? So we did geography equals county. That makes sense. I have a guide in the tidy census documentation, and I'm going to go ahead and pop that open in a new tab and grab the link for that and put it in the chat. So this table is going to be really useful for you. If you scroll down here and look at geography and tidy census, it gives you all of the different geographies that are available in tidy census. And you would plug that into the geography argument. So you'd say something like geography equals US. That gets you data for the entire United States. Geography equals state. That gives you data for at the state level. Geography equals school district unified. That'll be a unified school district, and so on and so forth. So you can experiment with plugging those in. This column here that says available by shows you that not all of the data are necessarily available at each sort of collection of parent geographies. So if a given value is bold, that means that the data are tabulated by that geography and require that geography to get the data. So for example, if you put in a census tract and you ask for census tracts, but you don't put in a state, it's going to error because census tracts require a state to get the data. You can optionally put in a county, but you don't have to. But if you're looking for census blocks, which is something that we'll cover in next week's webinar, you need to put in a state and a county to get that data. And so jumping back here now to the slides, that's how you get that geography identifier. And so you can use that to query information by state, query information by county. And a great thing about that is you don't need to know the FIPS codes. I can never even remember the FIPS codes except for the places that I've lived, and sometimes I don't even remember that. And so let's say I wanted to get small area data. So at the census tract level on median home value in San Diego County, California, I could use this code. So I'm using getACS, but I specify geography equals tract. I specify state equals California and county equals San Diego. And so if we jump back now to our studio, we can look at this data. So we pull that down, we get the data immediately. And so now we have data for all of the census tracts, which again are approximately neighborhood level units in San Diego County. So this census tract here, the median home value, it looks like is about $1.8 million. For any of you from Southern California, these values are going to be quite familiar to you as they're likely to be very high. And so I've seen a variety of questions come across the Q&A about, well, how do I know what B25, how do I know what this means? B25077, how do I look that up? Is there a data dictionary? What do I do? Well, I want to show you how to do that. There's a built-in function called load variables. And admittedly, this is one of the most difficult aspects of working with census data, especially for beginners, figuring out how you even find the data that you want. And I include the load variables function in tidycensus to try to make it easier for you. But there still are going to be limits to how easy it can be. And I'll explain why that is in just a moment. So if we run the load variables function, I'm going to assign it to an object named vars here, and then we can use the view function in our studio. That gives you an interactive data browser that allows you to sort and filter your data. And you can actually use that on your data as well, which I'll show you in just a moment. And so if I jump back here, I am going to uncomment these lines. And I'm going to go ahead and run this code. This pulls down the data dictionary for the 2023 5-year ACS. And as you can see here, you get an interactive browsable table of 28,261 unique variables you can get from the ACS. That's admittedly a lot, but you can see here 4 columns. In the name column, we see the name or the variable ID. This is what you'll supply to that variables argument in getACS. So if I wanted total population, I could use B01001 underscore 001, and I would get that data. If I wanted the total male population, I would use this variable. If I wanted the total male population under the age of 5, I would use this variable, and so on and so forth. In the 5-year ACS, not every variable is available for every geography. And so I include this geography column as a little heuristic. It doesn't mean this variable is only available at the block group level. It means that it's only available for geographies as small as the block group and up. So these variables go all the way down to the block group level. You can get them at every single geography available in the ACS. other tables, so if we scroll down, this is a breakout by race ethnicity. So sex by age, white alone. You'll notice that that is only available at the census tract level and up. So anything census tract level and larger, you can get the data on age breakouts by race, but you can't get that information at the block group level. That is, again, for statistical reliability and privacy purposes. And so there are some variables that are only available for the entire US. You'll notice me clicking around. There are a bunch of variables here, movers between regions in the United States that are broken down by demographics. Those are only going to be available at the US level. And so, that's something to be aware of when you're doing this sort of analysis. But you might say, okay, this is all well and good, but I still don't know. I want to look up income information and I don't know how to do that. Well, in our studio, here's what I recommend. You have two different ways that you can filter your data. So you have this little search box that you can use. And if you type in a query like income, it's going to filter down your data and search for that particular keyword. And so I typed in income, and now I have values on income for about 5,000 variables. So I've gone down from 28,000 all the way down to 5,000. 5,000 is still a lot, but it's a lot lower than 28,000. And just from a timing standpoint, by the way, so the first hour, we're going to go all the way up until 1 p.m. Eastern time, and that's when we'll break. And then we'll break for 10 minutes and kind of go with that schedule because we have all of that set up that we have to do at the beginning. And so you'll notice here for any of these variables, you'll see a label and a concept. And so the label tells you what the given variable means, and the concept tells you what the concept belongs to. And so I should show you this going back here. In this particular case, we have here estimate total male in sex by age, and that is for all race ethnicities. So this is the male population, but it's for the entirety of kind of the overall population. So all people who marked male on their form. And so that's our male population. If you scroll down, you'll notice that the concept changes. So here's the male population, but it's sex by age, white alone. So this is a cross tabulation. It's all the estimate of people who marked male on their form and also white and no other races on their form. And so that gives you a little bit of a nuance. And some people ask me, well, why do you make me put in the variable ID? Why can't I just put in white males if I want the white male population? Well, the problem is you'll see that these labels are duplicated across tables. And so I require people to be specific. And, you kind of need to do your homework a little bit to find what you want, because if you go in and you pick something, you accidentally pick the wrong thing, then now you're reporting on something that is inaccurate and you didn't mean to. And so that's something to be aware of. So going back to searching for variables, I type in income here, and then you'll want to think about how to filter that down further. And you can filter on these various columns. So if I want to click this filter button here, I can filter on the label or the concept. Let's say I want to look for median. And so just by putting in income here and median here, I've now filtered down from 28,200 entries all the way down to 124. And 124, that's something I can start manually browsing. So I can start going through and seeing potentially what I want and picking, do I want median non-family income, family income, household income? I've got all those variables available to me here. All right. So hopefully that's helpful. The view function is also available by clicking on any of these tables. And so something that is interesting, if you're curious, well, what is the most expensive? What is the most expensive in county in the US, I can click on any of these columns and I can sort them in ascending and descending order. So I click there. It looks like the most affordable county in the US is Todd County, South Dakota, closely followed by Oglala Lakota County. Those median home values there are around $45,000. On the flip side, unsurprisingly, the Bay Area, San Mateo County, Marin County, California, with median home values around or above $1.4 million. All right. So moving along here, I've got a couple more examples that I'll want to show you before the break. There are a variety of different ACS data sets available for you. And if you're looking up variables in load variables, you can look up variables by adding /profile for the data profile. And the data profile is really handy. It's available for the census tract level and up. And what you have to do, and basically that gives you pre-tabulated estimates in many cases, collapsed categories and percentages with appropriate denominators. So that can be really helpful to work with. The subject tables, comparison profile, and supplemental estimates, along with migration flows data, that's all available in tidycensus. So feel free to explore. All right. Beyond that, just a couple comments about data structure in tidycensus. So tidycensus is called tidycensus because it's designed to integrate with the tidyverse, which is an extraordinarily popular set of packages and framework for data wrangling and data analysis in R. And the idea behind tidycensus is when you grab data, it returns you a tidy or long form data frame where data are basically stacked by row. And so let's say I want to get that whole table of data on age and sex breakdowns from the 1-year ACS by state. I could supply this code here, and let's jump over to R and try that out. And I do notice one good question that I'm going to go ahead and clarify for you in just a moment. I go ahead and run this code here. I'm pulling down all of this data, and I can look at my age sex table. In fact, I'm going to pull that up here. So I have my data now stacked by state. So if we look at our variables here, we can get a little bit of a sense of what the concepts are. So this first one here, that's total population. Looks like this is the total population here of Alabama. This next one, that's the male population. This is the male population under age 5. This is the male population age 5 to 9, and so on and so forth. And so you can, go back and forth and align. I saw one person that said, how do I get the variable labels? You can join this data set if you want to over to your data set. And I'll show you how to do a join in the second hour. And that's one way that you can get the labels in there. That's something a lot of people do. I don't include that as a feature in tidycensus, just because, I kind of like people to do that themselves so that they are really fully aware of what their variables mean. And so you'll see this information stacked, and we've got now 49 different rows for Alabama. And then we get to the next state, Alaska, and so on and so forth. A lot of people who work with tidycensus, though, this is not the format that they like. This is the format I personally like, and that's part of the reason I developed the package and called it tidycensus. But a lot of users prefer wide data. This is what they're most useful when they're downloading data, where the variables are not stacked in a variable column, but rather they're spread across the columns, and each variable gets its own column. And so if you specify output equals wide in your call, what you can do is you'll get the data back, and it's going to look like this. It's going to be spread out. And you'll notice here when we jump back and I run my code, if I want my wide data, it's going to pull down the exact same data. But when I open it up here and take a look, it's going to look very different. So I now, instead of having 49 rows per state, I only have one row per state. And then I have all of those variables spread across the columns. And you'll notice I get a separate column for E, the estimate, and M, the margin of error. And so in this case, total population is a controlled estimate. So you can have confidence that that's the true value. These other estimates have associated margins of error. And tidy census as a design decision always returns the estimate and the associated margin of error. And that's in part because my personal belief is, we often treat ACS estimates as if they are true counts. They are not. They are modeled estimates based on a survey sample that are characterized by error. And so understanding the uncertainty around that is, in my opinion, very important. So jumping back to the slides, got one more example for you, and this actually answers a recent question. So can multiple variables be specified at the same time? Absolutely. What you'll use is a data object called a vector in R, which is a type of object that can store multiple objects inside of it. And vectors can have named elements. So you can say something like, you know, fruit equals X, vegetables equals Y, bread equals Z, something like that. And that will give you a name that is associated with an object. And so jumping over here, I'll show you how that works. And you can see I specify, let's say I want educational attainment percentages from the data profile in California. I can specify geography equals county, state equals California, and then I specify a vector, and you make a vector with the C function. So if I do C, percent high school equals this variable, percent bachelor's equals this variable, and percent graduate equals this variable, I'll get a data set that looks like this. And if I jump back and give it a try, I'm going to go ahead and run this code. I'm pulling down that data and I see one question. Could you remind us how to look at the whole table instead of just the results in the console? So you can either go to the environment tab here and you can click on the corresponding data set. So my data set is called CA Education. I can click on that and that shows me the entire table in this interactive data viewer. And so you'll notice here for each county, I have 3 variables, but those variable IDs have now been replaced by the names that I gave it. So instead of a variable ID from the ACS that I might not remember or people might not understand, I get percent high school. So Alameda County, California, 15% of the population, their highest level has a high school degree, and that's their highest level of educational attainment, 28.7 a bachelor's, 22.8 with a graduate degree, and so on and so forth. And so, all that information ends up, being, very useful to us to kind of be able to go through and use. And hopefully you get a little bit of a sense here of some of the various ways that you can work with ACS data using tidy census. And so let's go ahead and take a 10-minute break. We'll reconvene 10 minutes after the hour. And jumping in here to part 1, just kind of thinking this through, a couple of things that you could do while you're waiting. And feel free to ask questions and I'll answer a few of them as well once we boot up again in 10 minutes. But try using that load variables function. Find a variable that interests you that you haven't used yet, and then try using get ACS to fetch data on that variable for counties, similar how we did earlier. So just kind of plug that in and give it a shot. So feel free to try that out. I'm going to go dark for 10 minutes. I'll be back 10 minutes after the hour for part 2. All right. Hopefully everybody had a chance to stretch their legs a little bit. A lot of you are still sticking around, which I really appreciate. And let's dive right back into it. So I'm going to answer a couple questions. Unfortunately, I'm not going to be able to answer every question because there are a lot of questions coming in, which is fantastic. Something that you can do is connect with me on social media. What I'm going to do, just so that you have it, is I would love to connect to attendees. So you can find me on. I message that directly to Jessica. You can connect with me on LinkedIn here. You can give me a follow over here. I post a ton about census data, and so if you want to stay up to date on everything that's happening, I'm on X and I'm on Blue Sky. So you can go ahead and connect with me or give me a follow at any of these sites, and I'll try to keep you up to date as best as possible. So, um, in terms of some of the questions, question is tidy census data already cleaned? The answer is yeah. That's a part of the idea behind it. So the raw data coming in from the Census API really isn't terrible, but Tidy Census is not returning raw data from the API. It does some light cleaning of it so that ideally it's ready to go for you to get to work with it. And so a lot of this is reshaping it into that tidy style format, that tidy format that I was talking about, and doing the wrangling to piece together the estimate and margin of error columns. I got another question. The variables don't change between states. No, they do not. Variables are the same variables all across the United States. The only caveat is in the data profile. There are some separate variables for Puerto Rico. If you're working on Puerto Rico topics, then there are for the rest of the US. But if you're working with the detailed tables like we've been doing, it's the same variables across the US. That includes Puerto Rico. And that allows you to do comparisons across states. So no, fortunately, you don't have to memorize a whole set of new variables by state. Another question, can multiple geographies be specified at the same time? The answer is no. You have to have only one geography at a time. This is for appropriate comparative purposes. Now, in theory, what you could do is pull multiple tables together and then combine them, but Tidy Census won't do that for you. Additionally, and we'll talk a little bit about time series analysis today. We'll talk more about it next week. You can't request multiple years at the same time. And this is in part because variables can change from data set to data set. And so that's just something that you'll want to be aware of. And so taking a look here, let's move on to part 2 and look at some ACS data workflows. So we mentioned before the 1-year ACS versus the 5-year ACS. And so the 1-year American Community Survey is fantastic for getting you as up to date of data as possible. So for any of you who have ever used census data in client projects, as I do frequently, you will always get from your clients, well, it's February 2025. I want data for February 2025. And so you hear that information, you think, well, that's literally happening right now. How am I supposed to have data? Because you have to go collect the data, and then you have to process the data, and then you have to, quality do QA/QC on it, and then you'll release it. And so there's always going to be a temporal lag, which of course your client is going to want information for right now because they're doing business right now. And so the 1-year ACS is great for getting you really as recent of data as possible. So the 2023 1-year ACS data typically comes out in September of the following year. So really you're getting about a year lag, but that's at least something that's reasonably close. But you only get that for geographies of 65,000 and greater, which so Only 854 of 3,222 counties are available. Only 649 of cities or census designated places are available. And again, that can vary from place to place. And so you can't get data for census tracts, block groups, zip codes, or any other geographies that typically have populations below 65,000. So you'll notice some changes. Now, I want to compare a table of data that we can look at from the 1 year and the 5 year ACS. So there are going to be values available in the 5 year ACS that may not be available in the corresponding 1 year ACS. So you may even say, okay, well, I'm trying to pull this variable and I know I can get it for this geography in the 5 year ACS. And I think that geography has more than 65,000 people. Why can't I get it in the 1 year ACS? Well, that may be because the estimate is suppressed just because you don't have enough statistical reliability or confidence to report on it. And so if that data is available, the margin of error around the estimate is going to be larger. So people often come to me and they ask, well, should I use the 5 year or the 1 year data? And I frequently say that depends. What is the highest priority for you in your analysis? Do you need recency? Is your client coming to you and saying, I need data for right now? And you can use stuff like the current population survey, but that's not very spatially granular. So they may say, okay, I want to know about the demographics as close as possible. And so you'll say, well, 1 year ACS might work. And in many cases, they might be interested in a city or a metro area or something like that. And you're going to get, for larger geographies, you're going to be able to get that information. But if they're more interested in statistical reliability, so they say, well, I really want to have confidence in this estimate. I want to make sure the margins of error are low. I want spatially granular analysis. Then you need to go to the 5 year ACS because you can't get spatially granular data from the 1 year ACS. And yes, there is going to be a temporal lag. So the 2019 to 2023 5 year ACS is the most recent that we have. And so that's based on pooling all the responses for those various ACS 19 through 23 and then reweighting them to align with the population composition of the US. And so you're going to have, responses that are informing those estimates that go all the way back to 2019. And so that's something to be mindful of. So we could take a look at this for a very small population group, Punjabi speakers by state. We can pull this from the 1 year ACS and you'll notice some data sparsity. So Alaska, we get NA, and so that's just missing data. That value has been suppressed. For Arkansas, we get 0 with a margin of error of 208. In other cases, the estimates are so small, such as for Delaware and the District of Columbia, that the margin of error actually exceeds the estimate. So this is basically saying, we think the estimate is 1,643 Punjabi speakers in Delaware, but it could be 0, or it could be over twice that. And that may or may not be a satisfactory response for depending on what you're looking at. And you're saying, well, we need to know how many Punjabi speakers there are right now in the state. Well, you might be okay looking at the 1 year ACS. That's going to be as recent as possible. But if you're just interested in comparing states and you want some more statistical reliability, you can use the 5 year ACS for the same thing. And that's going to get you some more reliability. So for Arkansas, instead of getting 0, we get 519 with a margin of error below the estimate. And so the margin of error now for DC, for Delaware is below the estimate. For Alaska, we get a value back. It's still 0. So there's maybe only a handful, but that gives us a little bit more reliability. And even for a place like California, that margin of error drops from 13,700 all the way down to 6,100. Now, we're not necessarily fully reflecting recent demographic changes then, but that still gets us a little bit more statistical power. And just for purposes of working through this, I can go ahead and show you what that looks like. Here's what it looks like um, if we go through and run it. So feel free to give that a try. All right. So let's spend some time now talking about visualizing ACS data. And we're going to look at visualization for a couple different purposes, thinking about making comparisons from a graphical standpoint. And then we're going to do some geographic visualization. And, for those of you who have been interested in what's been going on with the census geographic data who are in attendance today, I'm going to show you a workaround that I think can serve as a stopgap for you to help you continue to do your mapping work for the time being. So let's get started talking about visualizing ACS data. And one thing to keep in mind when you're visualizing ACS estimates, and I've said this before and I will say it again, is ACS estimates are estimates characterized by a margin of error. And that means that when you are visualizing differences between different estimates, those comparative visualizations can be misleading if you're not referring back to the margin of error. And we all want to see rankings and ratings, and that's all really important for decision makers. Oh, are we higher or lower than this place? What is the top? What is the bottom? In terms of this particular attribute or variable of interest. And I totally get that. I want to walk you through an example that illustrates how to communicate this information while still communicating uncertainty. So let's do a walkthrough building a margin of error visualization with ggplot2. This is one of my favorite types of visualizations. I do cover it in the tidycensus documentation and in my book. I want to step you through how it works here. So we're going to grab some data on median household income by county in Utah. And we're going to assign it to the object Utah income. So let's jump back and let's go ahead and run that. And so now we have this object Utah income. I'm going to take a look at it. We have 29 counties in Utah, and here's our data set. And so we can do a little ranking if we want to. Frankly, if I wanted to know which county has the highest median household income in Utah, I could sort in descending order. And it looks like it's Summit County with an estimated median household income of $137,000. We notice the margin of error around that estimate. What's interesting about this, though, if we look closely, is we might want to do some rankings. And you see here that Beaver County, Utah is the 10th wealthiest county as measured by median household income in the state. But is it? The estimate is $85,603 is the median for a household in Beaver County. But the margin of error is nearly 14,000. And so margins of error reported at what we call a 90% confidence level by default in the ACS. And so you can interpret that roughly as we are 90% sure that the true value of median household income for Beaver County is about $85,600 plus or minus about $14,000. So we're 90% sure that it falls somewhere in that range, which for those of you who want crystal clear certainty, maybe that feels a little unsatisfying. But again, we're working with survey data. We're not asking every single American these questions. As such, we have to make estimates. And that's what the ACS is doing. What that means is that while Beaver County, the point estimate ranks 10th, Beaver County, if we were to add $14,000 to this, Beaver County could be as high as 5th, could be as high as 6th, or it could be as low as 17th or 18th. It's somewhere in that range. And so how do you communicate this information? Well, I want to step you through a potential workflow that you can use. So jumping back here to the slides, let's go ahead and talk through this. So ggplot2 is, I believe, the most downloaded R package. Just pulling this up in another tab. Tidycensus has done well since its inception. And I mean, it's been downloaded nearly 600,000 times. That makes me feel pretty good that it's been downloaded that many times. Well, ggplot2 has been downloaded about 156 million times. So if you're thinking about scale there in terms of the packages I've developed versus ggplot2, it's not even close. So ggplot2 is the most downloaded R package ever, nearly 156 million downloads, and it is widely recognized as one of the premier frameworks out there for visualization of data. And so to visualize a data set with ggplot2, we define an aesthetic mapping and a geom. And so basically what we're doing here is we'll load in the ggplot2 package, and we initialize our plot with this function called ggplot. We pass to it here a data set and then an aesthetic mapping defined with AES. And an aesthetic mapping is basically what that does is you have different elements of your plot. You might have an x-axis, you may have a y-axis, you might have a fill color or an outline color or an opacity or something like that. And what you can do is you can map columns in your data set to those various properties. And so in this case, we are mapping the estimate column, which is our estimated median household income, to the x-axis. And then we're mapping the name column, so the name of the county, to the y-axis. Once we do that, we then need to draw a geom, draw some sort of shape on the plot that draws from that aesthetic mapping. And here, when I specify geom point, it plots a little circle that corresponds to the intersection of these values. And so just to show you how that works real quick, I'm going to go back here to the code, and I'm going to load this in and run this chunk of code here. And I'm going to assign it to the object Utah plot. And then I'm going to go ahead and run Utah plot, and you'll see here this plot. Make this a little bit bigger so you can see it. So the plot in and of itself, you'll notice, is organized in reverse alphabetical order because we haven't specified how to sort it. And so this does visualize median household incomes by county in Utah, but it doesn't do so all that effectively. The data are not sorted, so it's difficult to understand the patterns. You can see which one has the highest value, that's Summit County, Utah. You can see which one has the lowest value, Paiute County, Utah, but the rest of it, it's kind of a mess. And so we're going to need to do some cleanup. And just to reiterate some of those problems, I already identified a few of them, but let's just go through this. The data are not sorted by value, so comparisons are difficult. The axis and tick labels are not intuitive. Now, we know what estimate and name mean because we're working directly with the data. But if you hand this off to somebody, they're not necessarily going to understand what that is. So we need to be more specific about that. The y-axis labels contain repetitive information. All of these are counties in Utah. We don't need to put County Utah every single time. All of that information is redundant. We'll likely want to remove it. And we've made no attempt to customize the styling. And one nice thing about ggplot2, it includes nice looking defaults in terms of styling. So we have the gray background, black dots. This isn't terrible in terms of styling. It's not like some of those awful, Excel 97 charts that you'll see floating out there. It has nice defaults, but when you just use those defaults, you're not making the plot your own. And I want to show you a few ways that you can customize this visualization. So let's take a look at this. We're going to add a couple things. We're going to use reorder to sort the counties by the values of their ACS estimates. So in this particular case, instead of showing just the name, we're going to show the name ordered by estimate. And then we're also going to change the color of our points to dark blue and make them a little bit bigger. So let's go ahead and try this out. I am going to change the plot here and print it out. And already it's a lot better. You can see that. There's still things that aren't great about it. Now our y-axis is reorder name, comma, estimate. We don't want to do that. You wouldn't hand that over to your supervisor, to your client, but at least we can make clear comparisons because the dots are a little larger. They pop a little bit more because we've changed the color, and they are sorted in descending order of the estimate column, which is very helpful for making comparisons. Like I can actually see, even though these dots are in very similar locations for Emery County and Uintah County, we know that Emery County is slightly more with respect to its point estimate. We're still going to want to do some additional customization though. And this is where we can add some custom programming. And for those of you who are brand new to R, some of this will feel a little bit more advanced, but hopefully it gives you a little bit of a sense of the power of what you can do. So what I'm doing here is I'm using a built-in labeling function and adding in call it to scale x continuous. So what I'm doing is I'm saying I want a continuous x-axis that I can customize. And I can go in, I can say, okay, I want the labels to use this label dollar function from the scales package, which will give me nice looking dollar formatted labels. Or I can define my own function where basically you say, I want the y-axis labels to be, and let me just translate this for you. For every value of x, for every value x, so my son is in 6th grade. He is learning basic algebra right now. And so we're doing all of this kind of stuff. I say, this is the kind of stuff Dad does his work, solve for x. That doesn't necessarily make it any more fun. But you can think about it this way. You can say for every x, so for every value on the y-axis, run this. Remove the string Space County, Utah from X. So it's basically saying remove all of this chunk of code that I just highlighted, Space County, comma, space Utah, remove that from every element in the y-axis. And so if we go back to R, we can run this through. So we're going to need to load this in. And you'll notice that already our y-axis tick labels and our x-axis tick labels already better. So we have nicely formatted dollar values using that built-in label dollar function. So that's really helpful. And now we've removed that redundant information. We still have some more modifications to make, but this at least is getting us well on our way. Beyond that, we want to make some additional modifications. And we can do that with the labs function. The labs function allows us to overwrite the labels of any element of our plot. So in this case, I'm adding a title, median household income in the 2019 to 2023 ACS. And then as a subtitle, I say counties in Utah. So that's something that still is helpful context to know. I don't necessarily want a plot like this that says County, Utah, County, Utah, County, Utah dozens of times. That's redundant. But I also don't necessarily want this plot because unless you're already familiar with the state of Utah, and I understand there is a Utah county, so you could probably guess it, but unless you are familiar, you're not necessarily communicating what those names are. So you still need some reference. We just need to put it somewhere else. And so in this case, we say the subtitle is going to be counties in Utah. A caption, we cite our source, data acquired with R and tidycensus. And then we map, and then we say, okay, the x-axis should be ACS estimate, and the y-axis, those are the county names. We don't really need to put a label. We then use the theme minimal function to change the default theme, and you can customize your theme of your plot as well to whatever you want. So let's go ahead and try running this. You'll notice it gets a little bit cleaner. And one of the cool things about our studio is all of these are SVG graphics by default. So they automatically resize as you resize the plots pane. So this is already looking pretty good. We have cleaned up all of those unnecessary elements of the plot that we had before. We've removed all of the redundant information and basically consolidated that into the subtitle. We have an informative title, an informative x-axis, a caption to cite our source, and we have nicely formatted tick labels. So this is a pretty decent looking chart. I could be happy with this chart. However, this brings back the question of margins of error. We already know Beaver County could be up here. It could be down here. We know that because we looked at the data already. So this ends up being an issue that we need to address. And in fact, this is not just true of Beaver County. It's true of many other counties as well. So we did this already, so I'm not necessarily going to do it again. But if we were to go down the list, you'll notice that the margin of error suggests that for many counties, their ranking could be different. So how do we visualize this in an intuitive way? What I like to do, and there's a lot more code here, so I'm going to step you through it, but what I like to do is create what's called a margin of error plot. And a margin of error plot, what that does is it allows you to go through and visualize the uncertainty around a given estimate. So frankly, and I'll show you one of the things about this that's kind of cool, you can actually step through this and add various steps to it. And this gives you a little bit of a sense of how ggplot2 works. So let's go ahead and jump back to RStudio, and this will be an interesting exercise. So we're making an object here called Utah plot error bar. And so our final result is going to look like this when we run all of that code. This is our final result, which gives you that margin of error plot, where we have for every county the uncertainty interval around it. So for Summit County, we know that the margin of error means it's plus or minus a given value. So we have here the point estimate, and then we have bars that represent plus or minus that value. So in this particular case, for Summit County, it's 137,000 plus or minus about 6,400. That's exactly. So this bar here is about $6,400, and this bar here is about $6,400. And so you'll notice that Summit County is definitely one of the two richest counties in Utah, but it's entirely possible that Morgan County is a little bit richer given the confidence interval. But because those intervals don't overlap for Summit and Wasatch County, we know that Summit County, we can be confident that Summit County is ahead of Wasatch County. So as I mentioned, I wanted to step you through this because I kind of just ran all this code so I could create it. But ggplot2 is very, very popular in part because of its design philosophy. It's based on something called the layered grammar of graphics. So that's where the GG comes from in ggplot, grammar of graphics. And the idea is that you initialize a plot and then you add on various elements of the plot as layers. So let me show you how that works, stepping through it bit by bit. So if I were to just initialize the plot here and run this bit of code without adding anything else to it, I get this empty plot. This is an initialized plot where I've mapped estimate to the x-axis and reordered name to the y-axis, but there's no data on the plot because I haven't specified any ways to visualize it with a geom. The next thing I do, and I'm adding to it with this plus sign, is I'm adding the error bars. So I'm going to run this here and I'll show you what happens. Now we plot the error bars. So you can think of me as stacking layers. So I have my plot template. I now plot all of my error bars. Next, I want to plot my points on top of the error bars. So we run that. I add my points. Now I'm going to start to do some of the cleanup. Let's first clean up the x-axis tick labels. You'll notice how they change. Now we clean up the y-axis tick labels. You'll notice how they change, and then that redistributes and allows me to more efficiently use space on my plot. That's another reason why you want to remove redundancy, because if you think about it, look at all the space that's being devoted to redundant information over here on the left side of the plot. Once I remove that, I now devote more of my plot area to the data itself, which frankly is what's most important. I then clean up the labels. And then finally, this actually looks pretty good with the gray background, but I'm a fan of white backgrounds. On my charts, I can change the theme. So hopefully that gives you a little bit of a sense of how ggplot2 works if you haven't used it before, or even if you have used it before. And frankly, it's infinitely customizable. And that's why it's been downloaded 156 million times. You can basically paint with it and create any sort of plot you want. This barely scratches the surface. All right. So jumping back here to the slides, we're going to get to a section that is particularly germane and maybe is the reason many of you showed up. So if you've seen some of my posts on social media and that's motivated you to join, so I developed a package called the tidyverse R package. It was really the first R package that I published for wide consumption. And I first published it 10 years ago. And it basically does now, well, it did, what it did back in 2015. And the idea was that it automated data pulls of census shape files, which are the geographic boundaries that represent all those geographies that we talked about. It automated those data pulls and it automated loading them into R. And so a fairly simple concept where you could say, I want counties for the state of Texas, and it just gives you that data set. You don't need to go download anything, unzip anything, load into a GIS. It just does it. And so in that particular case, Tigris has worked. I've updated and maintained it over the years, added new data sets, added some new functionality, but it's basically the core functionality has been around for, 10 years. And Tigris, the package, has been downloaded now 837,000 times over the last 10 years. So it's been a pretty popular package. As of right now, that package doesn't work. And so tidycensus originally, and it will again, one of the best features of tidycensus was that you can throw in the argument geometry equals true, and that calls this underlying Tigris package just to pull in the shapes. So if I have a data set of counties, I could just get the boundaries of the counties along with it and make a map just like that. And then, in past years, it's been a core part of these webinars. But as of really a couple of days ago, the census geographic shapefiles used by tidycensus have been taken offline. And they've been taken offline to, as far as I know, what I'm hearing from the Census Bureau, comply with the executive orders from the president. It's not entirely clear what they are being audited for, but as of right now, they're not available. And until they are reviewed and approved, and I don't necessarily know what that means yet, but until they're reviewed and approved, they won't be back up. So a lot of people have been messaging me and saying, I depend on this for my job. How do I get the data that I need? And I'm going to be showcasing a variety of workarounds over the next few weeks. I'll be highlighting one today that I personally find pretty intuitive, and if this ends up being an issue longer term, I may end up incorporating into the Tigers package so we can get this functionality back online. So let's grab a data set. We'll grab information here on educational attainment in Cook County, which is Chicago by census tract. And so, we can pull that information down, and, just as to review, if we want to grab data profile variables, do dpvars is load variables 2023 ACS 5. And this is how you get from the data profile. There was one question about that. When would I put in /profile? It's when you want to look up data from the data profile, and there's a bunch of variables that you can look at. And there's only 1,300 variables in here, so you can browse it pretty quickly. I'm going to go down to the educational attainment variables just so we can take a look at it. But if we look here, we're grabbing from this specific variable, and that's the educational attainment. So for the population 25 years and over with a bachelor's degree or higher. And that's something that's pretty handy, because if you were trying to create all this information yourself, you would need to pull the data down and add up various categories and divide by an appropriate denominator. This is a pre-computed estimate for you that already gets you the percent of the population with a bachelor's degree or a bachelor's degree and a graduate degree as well. And so that ends up being something that's pretty interesting and important, and we can pull that down fairly readily. So we grab this information for Cook County, Illinois. We'll go ahead and run that. We have our data, and we can go ahead and print that out and take a quick look at it. So this is what our data looks like. Some census tracts, bachelor's degree attainment, Chicago is quite high. In other cases, it's going to be a bit lower. We can also take a look at some of the spread by sorting. So it goes as low as 1.8% of adults age 25 and up have a bachelor's degree, and it goes as high as 94.5%. So we have huge spread. You have some census tracts where nearly all adults have, or everyone above age 25 has at least a 4-year degree. And then you have other census tracts where it's extraordinarily rare, 1 in 50, if that, have a bachelor's degree. But when you're dealing with census tract level data, we can try to analyze this, but if I'm making, say, a plot like I made for counties in Utah, that's not going to be all that intuitive. Because for one, there are 1,300 census tracts, not 29 like we had for counties in Utah. And unless you know intimately the census data for Chicago, which I suspect that almost no one in Chicago even does, you don't know where these places are. Where is census tract 8275 in Cook County? I don't know. I suspect almost nobody knows. I suspect most people who live in that census tract, they don't know the ID of the census tract they live in. I use census data all the time, and I don't have that information memorized. Where it gets useful when communicating this information is when you can plot it on a map and actually show where it is. That's something that people understand. So tidycensus tries to make this easy. Unfortunately, some of that functionality is broken at the moment, but we can find a workaround. So while all the Tigerline shapefiles are currently offline, they are online from an API. the Tiger Web API. So tidycensus pulls from the census shapefiles on the Census FTP server. It doesn't pull from the Tiger API, but there is an API. And as of right now, it's not down. So a relatively new package named arcgislayers allows you to interact with Esri, which is the big GIS company, web services. And Esri's services or servers power a lot of government data sets, not just US federal government data sets, but also state and local data sets. And so some of this is maybe a little bit beyond the scope of this webinar, but the Tiger Web API is really handy for pulling this geographic information. And what I'm going to do is I'm going to jump over and grab this link and paste it into the chat. And so that'll bring up this web page, and I'm gonna just pull that web page over so you can see it. You can still get all of your census spatial data. So if you go down here and click Tiger Web REST Services, you're gonna see all of that spatial data. So this is all data that you can get from the Census Bureau. The nice thing about Tigris and tidycensus, it makes it that you don't have to get into the weeds with this stuff. And so I would like to try to make this a little bit easier. But if you need any of this geographic data, it's still up and you can grab it with the ArcGIS package. And so just to show you briefly how this works, what I want to do is I want to grab, and I'm going to jump back here over to Chrome. So let's go back to the slides here. Pop that there. I want to grab census tract data for, in this particular case, Cook County, Illinois. Again, tidycensus makes all of this easy where you don't need to know the FIPS codes. I'm going to try to make it easier for you again, but we have to see how things play out over the next few weeks. So when we go back here, we see that we used the FIPS code 17 for Illinois and the FIPS code 031 for Cook County. So that gives us some information that helps us understand what data to pull in. If we look here, we're using this arc read function in arcgislayers. And we're pulling from a web service URL. And you might say, well, how do I know what that URL is? If we go back to here, we can look through and find the information we want. And so I'm going to grab from the generalized services here, because those are going to be more nicely kind of visually formatted census tracts that are clipped to the US shoreline. And I can click there on census tracts and blocks. So this is the link that I want, and I click. And then this gives me all of the services that belong to that kind of family of services. So in this case, I want census tracts. I can get at a 1 to 500K resolution or an even more refined 1 to 5 million resolution. I'm going to click here. This is the data set I want, and then I can fetch this URL from the URL bar. That's what I'm going to use and plug in. So now I go back to R and I can run this through. I need to load in arcgislayers first. It's pretty fast. And I get back this spatial data set that I would have been able to get otherwise with the Tigris package, but I'm able to use it now. So from there, I can merge my data together. And the way I'm going to do that is using this left join function. And so basically what I'm going to do is a little bit of data wrangling. And I haven't introduced a ton of data wrangling in this webinar. It wasn't originally going to be a part of what we were doing today, but I want to show you how to do this. I'm doing something called a left join that's allowing me to merge my data sets together based on this column, common GeoID column. And once I do that, I'm going to go back to R and show you how that works. I now have a spatial data set where I've attached the geometry. So these are coordinates of all those census tracts to my data. What that then allows me to do is visualize it and make some maps. And the handiest way to quickly visualize data spatially is with the map view package. And the map view package is a simple, well, it's not a simple package, but it makes it simple for you. It is a data viewer, a spatial data viewer for R. And all you have to do is say map view this. And once you do that, you get an interactive map that looks like this. So let me show you how that works. I can use map view to make an interactive map of my census tracts. I can click on any of those tracts and I get the underlying data and information. Or I can specify a Z column that allows me to, in this case, create what's called a choropleth map and visualize the ACS estimates based on by census tract based on their values. And so that gives me the opportunity to do some data exploration. And here I have an exploratory map where now I can actually look at some of those patterns. And so you see these bright yellows downtown in the near north side of Chicago. That's where we see our high levels of educational attainment. West side and south side, that's where some of those values are lower. We have some pockets in here like Oak Park where it's very high. We have parts of the suburbs where it's a bit lower. And so those patterns are ultimately really meaningful, but they come to life when we make a map. And that was one of the original goals of tidycensus. I'll make it work again. We will just, it will require some additional development time and we'll see if those files come back online. A couple other things before we break, before the third hour, and we'll jump back here to the slides to do that. You might ask the question, what about mapping 1-year ACS data? Well, typically it is difficult to map 1-year ACS data because you don't have complete spatial coverage due to the population restrictions. So let's take a look at an example. Let's say we're trying to map the exact same education data, but we're looking at it by county for the state of Texas. So I've just kind of generalized some of this code here. I'm not going to step through that again, but what this is going to do is it's going to pull in the county boundaries and then join our education data to those county boundaries. And so if we jump back over to R and give this a try. So we're gonna pull in our demographic data, pull in our spatial data, join them together, and then map them. You see the issue, right? Only a fraction of counties in the state have populations of 65,000 and greater. So Texas has 254 counties. It's a lot. It's more than any other state. And most of those counties have small populations below 65,000. And so they're grayed out because we simply don't have data from the 1-year ACS for that. So when we're looking at spatial patterns, you can't really get a sense of those patterns using this sort of geography. And so a workaround I like to use is something called the public use microdata area. If you need complete coverage for your maps for the 1-year ACS. They're typically used for microdata geography, which is something we're covering in the next hour, but I find them really useful for mapping, say, real estate submarkets or urban planning areas or something like that. And so here I'm making a map of work from home for the state of Texas. Let's give it a try. I'm going to go ahead and run that and merge it in. And so I'll show you what Pumas look like. So this is 1 year ACS. So a Puma might contain multiple counties. So this entire area of Northwest Texas is a single Puma because Pumas have population sizes between 100,000 and 200,000. But we get complete spatial coverage now, and you can zoom in here, say to Austin, and this is the percent of the workforce that works from home. You even get sub-city granularity in large metro regions. So if we go up to the largest metro in Texas, which is Dallas-Fort Worth, we actually are able to see some regional patterns where the northern suburbs have as many as as much as a third of their workforce working from home. All right. So that takes us to the end of the first the second hour. I'm going to skip past this time series analysis piece. You can read through that, just something to be aware of, but I want to go ahead and take that break. I'll put in some part 2 exercises, but I'll be back in about 10 minutes, so 10 minutes after the hour. And we can conclude today's webinar with some discussion of ACS microdata, which might be a new topic to some, but it's a lot of fun to work with. All right, welcome back, everyone, and hope you're able to take a little break. And we'll go ahead and close things out with the final part of our workshop, which will be covering working with ACS microdata. I do want to cover a couple questions that have come up. Unfortunately, if you're having technical problems, that's not something that we typically can debug live in a webinar because there's so many different reasons why something might not be working. Typically, you'll want to make sure that you have all packages installed and updated, and that solves a whole lot of problems. But yeah, otherwise, unfortunately, we can't provide technical support because it's very difficult to understand the kind of underlying issues on a given user's machine. Um, a few questions that I think were particularly interesting that we can talk about. One mentioned, and I skipped over the time series, so why don't I just jump back and talk about this? Um, if you're trying to do time series analysis, a lot of people like to do this, especially with the 1 year ACS or with the 5 year ACS even. Variables in the data profile and subject tables do change over time. And this can be surprising and sometimes frustrating, where you're trying to pull for a given variable, say from the data profile from 10 years ago, and compare it with the most recent data, and the values are completely nonsensical. And the reason for that will be that the variable ID 10 years ago doesn't represent the same thing as it represents now. So they do move those around. And so that's just something you need to be aware of and make sure you're checking with load variables when you do that. I mentioned the Connecticut issue, but I didn't clarify that. So this is something that's pretty fun and fun in a sarcastic way. So if you're working in Connecticut, I'm just gonna throw some code up there um, to take a look at that. Like let's say we wanted to look at educational attainment by census tract in Connecticut. So I'm just gonna grab this and I'm gonna go down to the bottom of my script and I'm gonna repurpose this code. So I'm gonna use all of this, but I'm gonna change this to call it CT education. I'm gonna change the state to CT. And I am going to swap. I'm going to delete the county and I'm going to run this through. So there's my Connecticut education, CT education. And so you'll notice here we have data for the capital planning region. Um, that's a county equivalent area in Connecticut. And in fact, I'm going to refine this a little bit further. I'm just going to change this to county. and we'll take a look at data by county. And so you have all of these values. So these are your 9 county equivalent areas in Connecticut. Well, let's say we changed this to 2019. Or frankly, we go back, let's just go back 2 years, 2021. And so now we're pulling not from the 2019 to 2023 ACS, we're pulling from the 2017 to 2021 ACS. We have 8 values instead of 9, and they are counties, not planning regions. Guess what? Connecticut, as of 2022, changed all of its census enumerations. And this is because in Connecticut, counties have no real significance beyond historical significance. So some of you who are attending today might be from Connecticut, you know this. Many of us live in states like Texas, where I live, where counties are actually meaningful as a sub-state geographic unit. Counties are not meaningful in Connecticut. And so the state of Connecticut decided to start aggregating its data as of 2022 to planning regions, which are actually salient geographies within the state, which frankly makes a ton of sense. The issue with this is if you're trying to do time series with Connecticut, everything breaks. Because if you look at it, when census creates new geographies, it doesn't just give that an old GeoID to that new geography, because all of these boundaries are now different. So it's not like they're just renaming Hartford County to the capital planning region. It's an entirely different geographic area. And so you'll notice that the downstream GeoIDs, because if you're looking at census tracts, for example, census tracts inherit the parent GeoID of the county in which they are located. And so if I were to grab this data at the tract level for the 2021 5-year ACS, all of the GeoIDs would be different. And so that's the Connecticut issue. So you have to be aware of that. Do I have a clear workaround for that for today? I don't. I may cover that in the webinar at the end of the month, some strategies for dealing with that, but you do need to be aware of it. All right. Also, the 2020 1-year ACS was not released because of the COVID-19 pandemic. So if you're trying to pull a clean time series from the 1-year ACS and you put in year equals 2020, for example, I'll show you what happens. If I try to do, let's say I'm trying to pull this, I'll do year equals 2020, survey equals ACS1. If I try to pull that, I get an error message that says the regular 1-year ACS for 2020 was not released and is not available in tidycensus. So you're going to need to interpolate between 2019 and 2021 if you feel that's appropriate to do, or you're going to need to skip over it. All right, so that gives us a couple pieces of information to think about. Let's go ahead and jump into part 3, which is working with ACS microdata. And if you haven't worked with microdata before, it's really, really cool. So I've been working with microdata since probably for 20 years now, since I was an undergraduate at the University of Oregon. It's crazy it's been that long, but I first started working with microdata 20 years ago, working with data from IPUMS, which is the Integrated Public Use Microdata Series, which is hosted at the University of Minnesota. And we'll be covering some of those data resources in future workshops. And so the microdata reflect individual level survey responses made available to researchers. They are privacy protected and anonymized. And so you're not necessarily, going in and getting a record where you can say, oh, that's this specific person. It's not like that. But it allows you to go in and get individual level records that in turn, because all of the different responses to all of the ACS questions are in there, and associated with an individual record, you can do much more detailed cross tabulations than you would otherwise do with what's available publicly in the published tables. So the one you can get the two flavors of PUMS data for the ACS. The 1-year PUMS covers about 1% of the US population, and the 5-year PUMS covers about 5%. So this is not the full American Community Survey, it's a subset of that. And well, you used to be able to get data downloads in bulk from the Census FTP server. That's currently down, but you can still use the MDAT tool on data.census.gov to pull the data. I mentioned IPUMS at the University of Minnesota. That's available as well. Or you can use tidycensus. And so I'm going to show you how tidycensus pulls that data right now. So how do you use ACS microdata in tidycensus? Well, there's a function in there called get PUMS. And we've been working with get ACS to this point. Get PUMS is slightly different because remember, we're pulling individual records now. We're not pulling aggregate data. And so you're not specifying a geography in which you're tabulating or aggregating data to something. And so within get PUMS, you'll specify one or more variable IDs, and I'll show you how to find PUMS variable IDs. And you'll specify a state or potentially state equals all to get all states. So the function defaults to the 5-year American Community Survey. And you can also get 1-year ACS data. Default year is 2023. If you want full functionality for the 2023 ACS, you'll want to make sure you have the latest version of tidycensus installed, which is 1.7.1. You can get PUMS data in ACS all the way back to 2005 for the 1-year ACS and 05 to 09 for the 5-year ACS, again, with the caveat that 2021 year data are not available. So let's go ahead and check this out. We're going to pull data for Louisiana from the 1-year 2023 ACS. And the variables we're going to specify here are sex, age, which is HP, and household type, which is HHT. And you'll probably ask, well, how did you find that out? I'm going to show you in just a moment. And so let's go ahead and run this, and I want to show you how it works. All right, so we pull this down. It takes a moment to download. And then we can take a look at our data. It looks like we have 45,026 records. And I want to step you through what you see here. The serial number, that reflects the serial number of the household. If it has GQ in it, that means it's a group quarters household, which means that these are people that live in group quarters facilities, so not traditional households. Might be a college dormitory, might be a prison, it might be a senior care center. So places where, the people, you don't have a specific household unit like you would in, your family's living in an apartment or living in a single family house or something like that. SP order refers to the order within a household. So 1 is typically your household head, and then 2, 3, 4, 5, depending on how many people are in the household. WGTP is your household weight. So PUMS are weighted samples, which means, and I'll explain how this all works, that each record represents approximately a given number of people, or each household represents a given number of households. Each record represents a given number of people. And in fact, to illustrate this a little bit more clearly, I'm going to bring up this data set in the data viewer, and we're going to sort it so you can actually see housing units here. So here we take a look at, this is a housing unit that appears to just have one person in it. And so in this particular case, the household weight is 79. So this household represents approximately 79 households just like it and approximately 78 people just like it. This person's age is 22. and then there's a given household type and sex. It's not clear what those values mean, but I'm going to show you how to get the value labels in just a moment. This is another single person household, but this person represents about 123 such single person households and about 123 people. And so in this particular case, this is a 79-year-old. You'll notice here is a household where the serial number is repeated. So we've got these here. This is a 5-person household in which the oldest person is 62, the second oldest is 50, and then we also have presumably 3 children of age 20, 15, and 14. So you can really get a sense of the types of detail of analysis you can do. You can do within household analysis, like household composition analysis. Given different demographic groups, how many kids are they having? That sort of thing. It's remarkably useful for understanding the dynamics and dimensions of the US population. So let's learn a little bit more about how to actually optimize our work with this. And just reiterating what you see, GitPums returns these technical variables by default. So SP order combined with serial number uniquely identifies a person, serial number uniquely identifies a household. WGTP is the household weight. You'll notice for group quarters, the household weight is 0 because they're not really considered to be a household if you're in a college dormitory. And then PWGTP, that's going to be your person weight. And so it's important to think about it this way. So each of those rows, again, if the weight is 100, then in the PWGTP column, what that means is that this row represents approximately 100 people in this area, in this case, Louisiana, with similar demographic characteristics. So that's the kind of thing that we're talking about here. And so we can go through and we can tabulate the weights. And something that you'll commonly do is you'll sum over that weight column to get demographic breakouts. And so, this is something that is interesting to take a look at. If I go back to my code here, which I'm going to do, I might be interested in finding out the overall population of Louisiana. And then additionally, the number of people in Louisiana that are the same age as me. So I'm 41 years old. And the overall population of Louisiana is something we can just pull from the regular ACS tables. That's available. But the number of 41-year-olds is not something we can pull. We can't get age breakout information at that granular level in the ACS. It'll be an age band, probably 40 to 44. The decennial census does have single year age band data, but the ACS does not. So you can't, from the published ACS tables, get a single year age band estimate, but you can do that with the PUMS data. So let's take a look at this, what the population is. So the overall population of Louisiana, by summing over that weight column, looks like it is 4,573,749, of whom 63,826 were 41 years old in the sample. So how do we know if this is accurate or not? Well, we can check by using getACS. We can check our answer. And so if I run that through, I should get the exact same number as this, 4,573,749. I got the exact answer. So what that means is you can have confidence that the PUMS data are weighted to align with the published ACS tables. Now, margins of error are going to be a little bit different because we're drawing from a smaller sample. So you're likely in those tabulations going to have larger errors around your estimates that you create. But in this particular case, I can't look up the number of 41-year-olds in Louisiana from the ACS. It's not in there. But I can estimate it in this way from the microdata. So jumping back to that point I made around, I'll skip over this. jumping back to the point I made around, okay, well, how do you know HP for age, HHT for household type? How do you know this? Well, there is a data set built into tidycensus called Pums variables. And that is where you go to look up variable names. So let's go ahead and take a look at that real quick. I'm going to jump over there. We're going to call this code here view Pums variables, and that will pull up our Pums variables. And you'll notice that we have a data dictionary back to 2017. We don't have a data dictionary before 2017 because the files, the census didn't provide those files before 2017. So we can't do that same kind of lookup for the earlier years, although all that data still is available. But I can go through and I can take a look at that. And I could filter on these different columns if I want. So if I want ACS1 for 2023, I can do that. And that's going to filter that down. And I've got a lot of different variables that I can draw from. It is a long form data set. And so you'll notice here that, say, the state variable has multiple rows. Well, that's because this data set provides you not just with the variable codes that you can use when you're requesting data, but it also provides you with all of the different values. And in this case, those are 2-digit state FIPS codes. And then whether you can do recoding with it. So if I start to go down here, I see a bunch of these household variables. So these are housing level variables. I get the acreage, so lot size of the property in which the household resides. And in that particular case, it can give me the various codes. Is it on less than 1 acre, 1 to less than 10 acres, or 10 or more acres? Got a ton of other stuff in there, such as access to the internet. So if you're analyzing inequities in internet access, you could say, okay, well, who doesn't have access to the internet? Who does, by paying a cell phone company or internet service, or without paying a cell phone company or internet service, and so on and so forth. And so if I go down here a little bit more, we were working with that HHT variable. So if I wanted to look at that, I could type in HHT. And I notice here that means household or family type. And I can go over and take a look at it. So a value of 1 is a married couple household. So that household of 5 that we looked at, that was a married couple household. Some of those other household types, they had 6. So it was a non-family household, female householder living alone. So you get a lot of this nuance in there where you can do some of these demographic analyses. And then you can bring in this information to your data by using recoding. And so if you use the argument recode equals true, you can append recoded columns to your data set based on the information in Pums variables. This is really handy because it's tough to even remember. I don't even always remember if it's just for a variable like sex, where the values are male and female. I don't even remember all the time is male 1 or is it 2? That's the kind of thing. It's handy to put in the recode. And so if I go back and rerun this, but recoding it, I'm going to run that through. I'm going to pull the data down. I can take a look at my data. And I see here that we've appended a household type label and a sex label. So I see here that sex of 1 is male, sex of 2 is female. Group quarters is on top. So I'm going to sort this in descending order so we can see. Okay. Female householder living alone. Male householder living alone. Female householder not living alone. And so you might have a non-family household where in this particular case, you have these 2 people. And it looks like we have a man and a woman, or excuse me, we've got 2 32-year-olds in the same household. But it's a non-family household. And so in this particular case, that may be a cohabiting household or something like that, but it's not a married couple household. And so you can see what the different values are. We have married couple household, other family household or male householder, no spouse present, female householder, no spouse present, and then a non-family household where you have a female householder living alone or not living alone. And so that gives you a sense of some of that complexity. But that recoding ends up being pretty useful, especially when you're doing some tabulations with your data. So when you're working with your data, especially with Plum's data from the 5-year ACS, those data sets can get pretty big. Like if you're dealing with California or Texas, or you need to pull data for the whole US, you're going to end up going into the hundreds of thousands, if not millions of records. And if you're just looking to analyze a subset of the population, that can be overkill, and those download times can be pretty long. So there's an argument in Git pumps called variables filter that sends a query to the API and says, okay, only give me back this specific set of information that I need. And then that can really reduce long download times. So you specify the variables filter as a named list. So your name is going to be your pums variable, and then your value is going to be, could be a vector of values that you're requesting. If you're new to R, some of that language may not make a ton of sense. So let's go ahead and take a look at this. So I'm grabbing data from the 5-year ACS PUMS here for Louisiana, same variables, but instead I'm specifying a variables filter. And that variables filter, it uses a structure in R called a list. And a list is a really flexible data object that can store basically whatever you want, and it consists of key value pairs. And so you're functionally saying, I want only, in this case, women, sex equals 2, between the age of 30 to 49. So I can jump back to R and run that code. It's pulling now from the 5-year ACS. And I can take a quick look at my data. And I see here that I'm only pulling for sex equals 2, and all individuals here in the age column, the age falls between that 30 to 49 age bracket. And so in this particular case, I can do that very tailored demographic analysis. And maybe I could look at, what do household types look like for women between the ages of 30 and 49, or anything else? What jobs do they have? What do incomes look like? That sort of thing. So this gives you a little bit of a sense of the flexibility of how you can work with microdata in this context. So jumping back to the slides then, we can look at some other functionality in the PUMS data. So I mentioned Pumas briefly in the previous hour, that are flexible geographies that can be used for the 1-year ACS. So Pumas are called public use microdata areas. And these are going to be the geographies at which you can identify people in the PUMS data. And so given that we have individual level records, privacy is paramount. And so we can't identify records in the PUMS all the way down, say, the census tract level. But we can identify them at the Puma level, which again is a geography of between 100,000 to 200,000 people. Pumas are redrawn every 10 years with each decennial census, but they tend not to go into effect until about 2 years after the decennial census. So the 2022 ACS was the first to use the new 2020 Pumas, and so on and so forth. The 2023 ACS, which we're talking about here, also aligns with the 2020 Pumas. What this does allow you to do is some granular geographic analysis. And so, in this particular case, if I had easier access to the geographies, I could show you. But in fact, let me go ahead and pull this up using some code that I did in the previous hour. So I want to show you what pumas look like in Louisiana. So these were the Texas pumas. We're going to jump down here, and I am going to grab myself a data set of Louisiana pumas. So I'm going to do where state equals 22. I'm going to paste this code into the chat if you want to run it through, because it is going to feel fairly new for many of you to work directly with these ArcGIS services, as it is for me, certainly. So I'm going to paste this code into the chat for you. And so see if that format's okay in the chat. But these are going to be your pumas in Louisiana. So you'll notice that in Baton Rouge, New Orleans, there's a little bit more granularity. In rural Louisiana, it's a little bit less granular. But I can click on any of these areas and it'll give me some information geographically on what it is. So this is Capital Region Planning Commission 6, Livingston and St. Helena Parish is Puma. Because in Louisiana, they have parishes as county equivalents. I could zoom into New Orleans here, and I could grab one of the New Orleans ones. Here we have Regional Planning Commission 7, New Orleans City Central. So that gives you a little bit of a sense of what we're talking about from a geographic standpoint. Some of those pumas a bit larger, some of them dividing up larger cities. And so if we wanted to get a breakout, say, of a demographic variable by Puma, we could specify the variable code Puma. Now, a quick heads up, for the 2022 ACS, it crosses over 2010 and 2020 Puma definitions. So the Puma variable won't work for the 22 ACS, but it will work or for the 22 5-year ACS, but it'll work fine for the 1-year ACS. And so we're going to go ahead and take a look at this real quick and run this code, Louisiana age by Puma. I'm going to pull that data down and then take a peek at it. And what this gives us is all of our individuals here, but then they're also identified by that Puma. And so this allows us to potentially tabulate data to these sub-state and in some cases sub-county geographies, which is handy because, again, a lot of these cross tabulations are not necessarily found in the published ACS tables. And so I do see a question. Could you please provide the link to Puma documentation detailed description? Unfortunately, all those files have been taken down for review by the federal government at this time. What I would recommend doing is two things. If you're interested in learning more about Pumas, I would direct you to my book, and I'm going to share a link for all of you right now. Chapters 9 and 10 of my book talk a lot about Pumas and microdata, so I'm going to pop that into the chat. And then I would also encourage you to go to IPUMS, which the URL I'm also going to paste into the chat. If you go to the IPUMS USA page, you're going to get a whole lot of more information about PUMS and Pumas. And so a lot of that information is going to be in there. Unfortunately, again, all of the official documentation from Census is up on that FTP server that's currently been taken offline. So we can't get access to that unless you want to go browse the Wayback Machine. So it is available on the Wayback Machine at archive.org if you want to take a look at that. So going back here to what we're talking about, you get a sense of hopefully how you can do some more, some geographical analysis. I mean, microdata is not great for geographical analysis because it's at a fairly coarse resolution, but that is for privacy protection regions. So, as we kind of round towards the end of today's webinar, I want to talk a little bit about how we handle uncertainty in these estimates. Because I had mentioned before that you're going to have more uncertainty in your tabulations from Pum's data than you would otherwise working with the uh, already tabulated ACS data, because it's drawing the from a larger sample size when you use get ACS than when you use get Pums. So kind of reiterating a little bit of that on this slide, but you can still calculate those standard errors and margins of error. And the Census Bureau recommends a formula using successive difference replication to calculate standard errors, and it provides replicate weights to do this. And so basically, I'm not going to get into the mathematical weeds of this, but the replicate weights, there are 80 additional weights that represent, again, some other, hypothetical population, like weights that could exist or the given individual that's in the record. And so you can use all of those weights to calculate standard errors and then margins of error around your estimates, your tabulated estimates with your PUMS data. And this is typically pretty hard to do, but tidycensus includes tools to try to make this easier and allow you to format your data for appropriate survey weighted analysis. So let's take a look at this. We're going to pull in replicate weights at the person level because what we're going to try to do is do some age tabulations by Puma from the 1-year ACS. We're going to need to get, a margin of error. We're going to need those replicate weights. So let's go ahead and run this through. It's going to take potentially a moment, depending on your internet connection, to run this because we're having to pull down a whole lot more variables. In this particular case, we're downloading the variables that you see up on the screen right now, but also 80 replicate weights. So that's a whole lot more variables. You'll notice that the file size is a lot bigger. And what tidycensus does that is nice, there's a variable limit of 50 in a census API call. What tidycensus does is it computes your request in chunks and then reassembles the results so you don't have to make multiple requests. So if we look at our data, you'll notice we have a whole lot of columns. We've got all of the data that we had before, but we also now have our weights column and then 80 additional replicate weights. So we're saying here, this particular person, our weight is 22, but could represent 4 or 5 or 35 or 20 people. These are all other hypothetical weights that could be used. And we could use that again to get a sense of uncertainty around any estimate that we compute. So we go back here to the slides and talk this through a little bit. The survey and surveyor packages are going to be your packages you'll typically use for survey weighted data analysis and handling of complex survey samples. And PUMS data represent a complex survey sample. They're individuals nested within households, nested within Pumas that have both household and person weights. And so there's a lot going on here that is essential if you're trying to understand not just tabulated information, but uncertainty around those tabulated estimates. So we can use the toSurvey function to wrap a lot of this functionality and create a survey object. And so let's go ahead and do that. And you'll notice our class is a table survey and a survey rep design. So it's incorporating those replicate weights. And so I mentioned before that, let's say we wanted to know the number of 41-year-olds in Louisiana. We can tabulate that fairly easily by summing over the person weights, but we don't have a sense of the uncertainty around that. And so we get by default a standard error, and you can multiply the standard error for a 90% confidence level by 1.645 to get your margin of error, like what would be reported in the ACS. And there's more information about that in my book, in the chapters that I linked, so feel free to take a look at that. But in the meantime, we can get a sense of the uncertainty. So 63,826 41-year-olds in Louisiana. Our margin of error around that, we're 90% sure that it's about plus or minus 6,000. So now we did a demographically granular tabulation, and we have a sense of the uncertainty around that, which I think is very useful. Outside of that, we can do all sorts of other tabulations. And so in this particular example, we might use a tidyverse workflow. And this is, again, we haven't covered a lot of tidyverse work and data wrangling in this webinar, but there is so much that you can do, especially with group-wise data analysis. So in this case, we're going to group our data by Puma, and then we can use the summarize command to calculate a median age. So in this particular case, we're asking, well, what is the median age in our data by Puma? So we use survey median to do an appropriate survey weighted median. So this is functionally a median weighted by that person weight variable that we have. And then we can figure out what the standard error and the margin of error is based on the replicate weights, given that we have set up our data appropriately. And so in this particular case, we jump back, we run this code, and we get a sense of median age by Puma, and then we get a sense of the margin of error around that estimate. I do see one question, and again, great question. We haven't covered tidyverse style data wrangling in this webinar. What you're seeing is a little bit more advanced stuff. You're seeing the use of the pipe operator. And so there are a couple different pipe operators in R. That is often used in data wrangling workflows to pass something from one line to the next line. So you can read this as the word then. You would say, take my survey object, then filter it for only those rows that have an age value of 41, then tabulate a survey weighted count, then create a new column named NMOE that is equal to the NSE column times 1.645. And so I would strongly recommend, because again, there's only so much time that and content that we can cover even in 3 hours. I would recommend taking a look at chapter 3 of my book, Wrangling Census Data with Tidyverse Tools. I go through all of this stuff. And so hopefully that can fill in some of those gaps. And the interesting thing about this, median age is something that is in the published tables from the American Community Survey. So we can check our answers and see how close we were. So let's go ahead and do that. I'm going to pull this data down. And so I'm going to type in LA age Puma. So I just pulled down median age data. And then I'm going to run this again as well. And we can make some comparisons. So, all right, so for Puma 00101, the published median age is 39.3 with a margin of error of 2.7. We got a median age of 39 with a margin of error of 2.9. Pretty close, not bad. So for Puma 102, we estimated 41 with a margin of error of about 2.1. The published estimate is 40.9, so very close, with a margin of error of 2.4. As you can see, in most cases, we're very, very close. And you might ask the question then, well, what should I use in this particular case? Should I use my tabulations from the PUMS data, or should I use the published tabulations in the ACS that I get from GetACS? And that's a good question. Typically, if you can get a published estimate from GetACS, that's what you use, because that's drawing from a larger sample than you have available to you in the PUMS data. And so whatever Census publishes, that's going to be more accurate. Where PUMS data become really useful is when you're doing those cross tabulations that you can't otherwise get in the published ACS tables. And so in that particular case, for example, if I want to know the number of 41-year-olds in my community or in a state, I can't get that from the published ACS tables. And so that's something I need to go answer with microdata. But if I wanted to know 40 to 44, that is in the published ACS tables. And what is published is likely to be more accurate than what I can do with my own tabulations using microdata. So, just the microdata are not going to be appropriate for every use case, but there are so many interesting things that you can do with them. And typically, I've seen them largely used in the academic social sciences, not as much in industry, but there's so many industry applications that you can use, when thinking about the types of detailed demographic analysis that are useful to a variety of different disciplines and fields. And so consider taking a look at it. I think, there's potentially a lot that you can pull. And so, yeah, so Chuck's comment, single year PUMS data, 1% sample, full ACS single year is about a 1.55% sample. So thank you, Chuck, for that context. You're absolutely right. Uh, and so you're not getting quite as much data that you're drawing from in the PUMS data as the full ACS gives you. And so, again, to reiterate, if the published estimate is available in the ACS tables, use that. If not, go ahead and take a look at the PUMS. All right. Well, that takes us to the end. And I'll look forward to see many of you next week. We're going to be covering next week the decennial census. So focusing on the 2020 census, but also we're going to do time series and think about going all the way back, potentially to historical data. We're going to see the evolving landscape of data availability as well. And I will continue to update data and advise you on how to handle any sort of restrictions because, it's a big priority of mine that we use this as a service to help you do your work effectively. And I know how many of you rely on census data, and so many people have been messaging me really worried. They say, well, I need this data for my job, for my research project, for my course, to get my degree, to make a key decision at work, and I can't do it right now. Well, I want to make sure that you have all the information you need so that you can keep, doing the important work that you all do. So thank you.